I think we can give this a go. All right, so good afternoon to everyone, and thank you so much for joining today on our third seminar in this new series. And before starting, I'd like to notify our audience that are present with us today that this session is being recorded and it will be uploaded to our website and YouTube channel. If you would like to, if you would not like to appear in the recording, kindly turn off your camera, please. So my name is Zach Shureb-Conti, and I'm a research associate at the Alan Turing Institute in London, although I'm currently talking to you from the island of Malta, uh, obviously for COVID reasons. I would also like to introduce my colleagues and co-organizers of the seminar, Andrea Pizzaferrato, who is an assistant professor at the University of Bath, and Temis Botsas, who is also a research associate at the Alan Turing Institute. So for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. For the benefit of those joining us for the first time, first of all, welcome. I'd like to briefly introduce you to the topic of this bi-monthly series, that is physics enhanced machine learning for engineering applications. Physics enhanced machine learning is an upcoming subfield in machine learning and deep learning that aims to integrate known physical understanding of observed phenomenon into the machine learning framework. And of course, the advantages of such an integration include data efficiency and also interpretability of the prediction models, which are vital and important criteria to real-world engineering applications. Um, Also, on a side note, if any of you are interested in sharing your work in any of our upcoming seminar series, please feel free to get in touch with us. We'd be really happy to hear from you. And also, as for the format of the seminar, our speaker will talk for around 30 to 40 minutes or 45 minutes, followed by questions and answers. And the questions may be asked by raising the hand function in the Zoom chat. Or preferably, if you do not want to ask the person with your camera on, you may also type the question inside the chat box. So without further ado, I'll ask my colleague Temis to introduce our speaker for today. And with that, I thank you all so much.
Thank you, Zach. Hello, everyone. Thank you all for joining in once again. Today, our speaker is Dr. Luca Magri, and Dr. Magri has a PhD from the University of Cambridge, a postdoc from Stanford University, various fellowships and other lecturer positions in the University of Cambridge and other institutes. He's currently a reader in data-driven fluid mechanics in the aeronautics department of the Imperial College. He's also a Turing Fellow and the group leader of the physics-informed machine learning and data assimilation under the data-centric engineering group. And according, he's also part of the, in a synergy with the Premier Group, which is an EPSRC grant. It's relevant on optimal design and multi-phase fluids. And today he's going to talk to us about physics-constrained reservoir computing for turbulence and chaotic learning. The floor is all yours.
Okay, great. Well, thank you. Can you hear me and can you see me? Well, okay,
All good.
great. Well, thanks much for the introduction, and I'm really happy to give this talk, and thank you also for the invitation. So I just put up these two figures, which are just scenic. One is physics on the E equals mc squared equation and all the others. And the other is from matrix, if you recognize that. I just couldn't think of a better example of data. It doesn't represent reservoir computing, but it represents the idea of data-driven methods. So the first things first, I'd like to thank my students and postdocs who are really the people behind some of the machinery I'm going to present today, and some of the sponsors who are sponsoring this research, in particular the ERC for the next 5 years, the Royal Academy for the past 5 years, and EPSRC, DFG in Germany, and Rolls-Royce for some more applications oriented themes. So I just wanted to first set out a little bit the philosophy of the problem. So what is the problem we are looking at here? There in the title there is turbulence and chaotic, and I just wanted to briefly summarize what is challenging about chaos. So As you know, maybe from dynamical systems or other, courses in science in general, in a chaotic attractor, if we take two close initial conditions, like the blue and the orange one in this attractor, at some point they will inevitably diverge from each other. So that's one of the possible and practical definitions of chaos, which is an extreme sensitivity to initial conditions and or any perturbation to the system through the parameters or through even some noisy forcing. This is sometimes known as the butterfly effect, introduced by Lorentz in the 60s. And that's a catchphrase to mean more mathematically that chaotic systems have an unstable tangent space. So that's really the property that makes these solutions deterministic, so in principle predictable, because they are a solution of an equation, but in practice unpredictable. So in this talk, I will focus on chaos and turbulence at the end, if I can get time permitting. And I would like to put emphasis on how can we predict chaotic systems, which seem to be intrinsically unpredictable. And we need also to specify what we mean by predict, which is what I'm going to do next. These applications, of course, I just showed the Lorentz system in the first slide, but chaotic systems are relevant to many applications, in particular from turbulence through aerodynamics, propulsion, and so on. Anytime we have a flow, which is my area of research, fluid mechanics, every time we have a flow which is sufficiently high in speed, it's very likely that the flow will become chaotic and turbulent. So chaos is difficult to predict, whatever that means. We will get there in a second, but before getting there, because chaos is complicated and difficult to predict, we need to leverage on, in my opinion, two different ways of modeling a problem and therefore predicting a problem. So historically, there are two broad categories of understanding the world, from Greeks, I would say. The first one is really empirical modeling, which is nowadays sometimes known, more broadly speaking, data-driven modeling. So empirical modeling is given some observables, given some observations of the reality. It's about finding the right correlation, the right function that describes the observations with respect to some inputs, some variables. That's very broadly put. So data-driven methods, for example, machine learning and artificial intelligence methods, they are great, therefore, at correlating, which is a thing that we will exploit today, interpolating as well. And they are great because they're adaptive. Anytime we have new knowledge, new data, we can reteach the machine, which practically is achieved by re-optimizing the machine to be able to predict more accurately the cost, the quantity of interest that we are looking at. The problem of data-driven methods, despite these capabilities, is that they are physics blind. They were born out of computer science, and by design, they don't see and don't understand what conservation of energy, conservation of mass mean. On the other end of the spectrum, we have physical modeling, which more philosophical is the kind of induction and deduction, to some extent, reasoning. So we look at reality, we try to distill some principles that govern the reality, usually very few principles. And from there, we translate principles into equations. So, and then we need to solve the equations by either pen and paper, or more probably for our problems with numerical schemes. So physical modeling, again, governing equations, partial differential equations, etc., they are great because they are not only correlating inputs and outputs, they are also enforcing causality. So this property is also useful because outside the range of observations, if the principles we selected are correct, or at least they are good to some extent, we can rely on the predictions of the model outside the range of observations. So it's very extrapolative until the assumptions, of course, we made in the modeling break down. The problem of physical modeling, as far as chaos also is concerned, is that they are rigid. What I mean by rigid is that they come from observations, then thinking from a human brain, principles, then translating principles in equations, finding the right stable numerical scheme to solve these equations, which in fluid mechanics is as important as finding the right equations to some extent. So if we find that at the end of the day, this model discretized with the numerics doesn't capture accurately the physics, then we need to rethink at this long stage where to change the model. And that's what I mean by rigid, as opposed to adaptive of machine learning. But of course, physical models are physics aware by definition. So what is physics informed or enhanced or constrained? From my perspective, I will probably refer to these terms as the same thing. Physics aware as well. Machine learning is just a machine that to different levels is able to either enforce some equations, therefore governing laws like conservation laws, or is such that the output is automatically fulfilling these equations. So that's what we mean by physics informed or constrained in this talk, machine learning. And the philosophy is that if we can use data-driven method capabilities and physical capabilities, what I try to do is to combine both to have a synergy. Right, to give you, this is the slide of the structure of the talk. It's quite perhaps overly ambitious, but I will try to cover all the topics. So in the orange boxes, you see the methodology I'm gonna explain. And in the light blue boxes, you see the applications onto which I will apply the methodology. Starting from the left column, we are gonna see the physics informed or constrained reservoir computing, in particular echo-state networks. And we are gonna apply that for the prediction of a small system, which is chaotic, for the reconstruction of unmeasured variables and the prediction in time of extreme events, deterministic events, which are very violent in the time series. In the middle column, we're gonna apply the physics-informed echo-state network to optimize a model combustor, so a simple model of a gas turbine combustor, which is part of my research as well with Rolls-Royce. And the problem we are looking at will be, physically speaking, what we call thermoacoustics. And in the final slide, in the final column on the right, we're gonna now extend the capabilities of echo-state networks from the temporal domain, from the time domain to the spatial and temporal domain to be able to predict spatially varying and time varying, of course, turbulent flows. Right, so I'll start with the first column, and I'll explain a little bit what is reservoir computing, in particular what is echo-state networks, which is technically a subset of reservoir computing, but that's what we use in this talk. So we start from the assumption that we have some data. Now, this array here of 4 little rectangulars represent just 4 observables at some time t. Now, the problems for reservoir computing, in particular echo-state networks we are interested in, is not just having some data, but is having some order within the data. So we work with time series of data, meaning that the order with which the data comes in is as important as the data itself. So that's an important thing. We want to be able to keep and learn the temporal correlation of the data. So we start from this, and the next thing we do, we take some data at time, say 0. And this is the input of our machine. Now, this data for this pictorial example lives in a 4-dimensional space, but it could be, of course, more than that. And what we do here in echo-state networks, we take this 4-dimensional input, and then we project out the input to a higher dimensional space. So that's perhaps the most important principle, in my opinion, of the reservoir computing framework for echo-state networks. I'll get back to that in a second. So from 4 dimensions, we project out to higher dimensions through a matrix Win. And in parallel, we assume we know the state of the system X. So U is the observable, what we observe with sensors and experiments. X is the state that is governing the dynamics of U. Now, this state X for time 0 is actually 0. So you can think of this as 0, but it will be helpful anyway to visualize it for later iterations. So the state is as big as the higher dimensional system. Then we apply a matrix which imposes some knowledge that we believe the dynamics has, which means we believe the dynamics of this higher dimensional state to be sparse, which is what we find in very many physical systems. And it's also to try to retain the low dimensionality of the original input to some extent. So now we have the two ingredients of basically, let's say, a scientific method. We have the orange, which is somehow related to the observables, what we want to match, and the state in green, which is what we believe it's governing the observables. So we combine them with an addition, and we saturate them with a nonlinear activation function. And this produces the state at the next time step, which is then projected back in the original observable space. So from higher, we want to go back to lower dimensional because we want to compare what we just estimated with reality, which is given by U. So W out is therefore a fat matrix, if you like, and it's the only trainable entity in this machine. So by projecting back, we get U hat at the next time step, which is the observables as estimated by the machine. We compare it with the observable from the experiment, from the data. We create a error, for example, just the usual mean square sort of error, regularized by some Tikhonov regularization, and we continue. The state of xn plus 1 becomes the input for the next iteration. We continue, therefore, for the sequentiality of all the data until the end. So we have basically the entire error that now we can optimize to get W out, to minimize the error. So in a compact form, this is sometimes just represented as the schematic below. We have input U that goes into a matrix, input matrix or input layer projected out in a big system. It creates a reservoir, which is the green circle, that is that sparse dynamics that we just described. And then it goes back in the original space with W out. So that's what you see in the papers, but this schematic is, in my opinion, not the best way to visualize the network. And it was proposed, this ecostate network, which is the open loop network we just saw, was proposed by Jaeger and Haas in 2004. So there are a few hyperparameters, and that's actually quite an interesting problem itself. We have done some studies on that, but I'm not going to actually cover the importance of the hyperparameters. In this talk, we will assume that somehow we got the right hyperparameters, but I'm happy, of course, to elaborate on offline. So now we have the open loop. The open loop was when we feed the data in the machine, and we continue feeding the data to create an error and then optimize W out. But what we want to do in prediction mode is really, okay, the data is over. We don't have data anymore. So the array, the white array is over at some point, at some time n. And we want to be able anyway to predict the future given what we learned in the past. So the prediction mode is very simple. We take the estimated output from the machine and we feed it back as an input to the machine itself. And if we've done a good job, then the output of the machine will continue following the right trajectory in the test set. Okay, and finally we come to the sort of a physics-informed ecostate network, which is the first architecture for today. There are other physics, let's say, informed ecostate networks to a different level. For example, the hybrid ecostate network by Patax et al. I'm going to focus on what I'm working on, which is what we call physics-informed ecostate network. So the scenario we want to reproduce is, again, we have the wide array of data, and somehow we would benefit greatly if we could sample or gauge or measure, if you like, where we don't have data, so beyond the extension of the data. So we create some collocation points in the future. So again, this is a time dimension. It's not a spatial dimension. We need to create some temporal collocation points in the future. and we run the machine in prediction mode autonomously. And this time we evaluate a residual of basically some equations that we believe modeling the reality, either like, you know, some residual of you can think of the easiest way as constraining the exact equations we know. That could be one way, or you can think of constraining a manifold, a small manifold of the entire equations as a residual. Depending on the level you constrain the residuals, you will have, of course, different accuracies and robustnesses. So this becomes from a linear optimization problem in the echo state, because it was only W out to be trained. So it's a linear ridge regression problem. Now it becomes a non-linear optimization problem if our equations are linear, which what happens for chaotic systems. They need to be non-linear if they are non-time delayed. Okay, so we have this architecture. We have there are the details on how to train it and the hyperparameters and all the machinery behind that. But I would like to show some applications on a small system, the Lorentz system, which is really the prototypical chaotic systems we want to play around when we test ideas and architectures for then scale up the ideas to more realistic systems. So the first thing I would like to show today is the capability of constraining the physics as far as filtering noise out of noisy data. So suppose the situation we want to tackle is ultimately the data comes from an experiment, and the experiments they contain some noise given by the experimental apparatus or other stochastic effects. So what we work on at the end of the day is some contaminated data. So data that contains the deterministic physics of the problem, the evolution, for example, of a turbulent flow. And on top of that, or also in a multiplicative way, some noise. So if we start from that, the idea was to try to extract from contaminated data the deterministic solution of a system. And the way we've done that was by assuming some noise, some model for the noise. We need to make some assumptions. And given this assumption, plug the data into the machine to learn the deterministic dynamics. So the solution of the Lorentz systems, if you like. So the results are in this picture here. I would start from the bottom, actually. The bottom is the mean square error, actually just the error in the test set. And the time is normalized by 1 over lambda max. Lambda max is the time scale for chaotic systems. It's the Lyapunov exponent that it's not the only time scale, but it's the easiest time scale that we can compute quickly for a deterministic system, chaotic system in particular. So if you remember the attractor, the Lorentz attractor at the beginning with the two trajectories, blue and orange, that they diverged, we can think of 1 Lyapunov time, 1 over lambda, as the time scale for which the two trajectories starts diverging from each other. So 1 Lyapunov time is really the best we can usually predict with time integration or other forms of modeling. So what we've done, we compared just the conventional echo state network, so without the physics constraint, in the red line in the bottom frame, and with the blue line, which is the physics informed. Without going into the depth maybe of the absolute numbers, the most striking thing is, of course, because we constrain some extra knowledge, we are able to extrapolate in time more accurately and for longer than the conventional echo state. In this case, actually, I picked a very, let's say, not the best result, because we are able to predict up to 1.5 Lyapunov times. And the reason is because we are working with noisy data. But we show that we can also extend it, depending on the size of the machine, up to 10 Lyapunov times, if not more. And on the top frame, let's just focus on one solution. Let's, for example, focus on the green solution. So in the green solution, you see no, maybe the red solution is better. Let me see. Now let's say red, because I can see better actually. You see a noisy line, which is the noisy data we want to filter out noise of. You see a black line, which is actually the deterministic solution of the system, which we are creating in a synthetic way. And in the dotted line, you see what the conventional ecostate is learning, which is something different, of course, from the deterministic dynamics. And you see in the dashed lines what the physics informed is learning. So in a nutshell, we are recovering quite accurately the correct result, which is the black line here. Now, we parameterize the problem with respect to different signal to noise ratios, and we saw some robustness on that. And we used only additive noise for this study. We haven't investigated multiplicative noise, and I'm sure there will be more challenges if we do so, and it's something that we are investigating currently. So physics constraint can filter out noise. There is work, of course, to do to see whether it does so for all the problems you can think of, but there is some, of course, good, kind of understanding that it can in principle. So the second thing we did was, okay, given a little more complicated model, can we predict some sudden oscillations that can happen in a chaotic signal? And this is called informally extreme events, where extreme events is, again, a deterministic event. So it's governed by partial differential equations with no stochastic effect, but it's a very violent, well below the average of the signal. That's what is an extreme event, nonlinear and high in amplitude. So to get things more in a fluid dynamics setting, we are here using a model for shear turbulence, wall-bounded turbulence. We have a simple model here of a flow which is coming from the left, flowing into this box where we have a wall here, a wall at the bottom, and this flow is forced by a volume forcing. So this is a prototypical flow that is interesting because it, again, models the shear stress dynamics of more realistic turbulent systems. What you see here, you see the extreme events, basically. The arrows represent the velocity of the flow. The surfaces represent the magnitude of the vorticity. And you see that in some moments, things seem to be quite quiet, like now. And suddenly there is a readjustment of the flow because of intrinsic instability for the streak mode and the vortex breakdown that happen very suddenly. So if you look at something from another point of view, the kinetic energy of the signal of the entire flow has this form here in the bottom figure. You see a lot of spikes. All those spikes are somehow an extreme event, which are not extreme, they're not necessarily rare, but they are well above the average of the signal. So the question we want to answer is, given some data and finding ourselves, for example, here, can we predict the occurrence in time and in amplitude of this upcoming extreme event? So what we've done first is just to understand how the machine works for this small turbulent flow. We are not looking into extreme events in this slide. We are just looking at the ability of the network to learn the dynamics of the flow. So we have 4 panels. Let's just focus on one of them. These panels represent different state variables of the system, but it's to make the point, let's just focus on this one. You can think of this as something related to velocity, if you like. So we have 3 lines. One is black, which is the data. So it's the, let's say, the truth, if you like. We have the truth here because we are creating the truth a priori to test the network. In red, we have the physics blind, if you like, ecostate network, and in blue, we have the physics informed. What you see here is really, well, all the 3 curves are different from each other, and we cannot draw any conclusion on the effect of the physics here. We can draw the conclusion, which we know already, that because of chaos, the solutions cannot indefinitely overlap each other. So even if you have the perfect machine with the perfect physics constraint, chaos will kick in at some point, and the solutions will diverge from each other. But the good thing is that, okay, the time-accurate solution of a turbulent flow or a chaotic flow is virtually impossible because of the chaotic nature of the signal. But what we are interested very often in as engineers is the statistics of the signal. So in this case, let's just focus on this one. We have the mean, so the mean profile of the axial velocity u bar with respect to one coordinate y, which was the vertical coordinate in the box I showed before. And yes, and for example, okay, I chose perhaps the smallest example. Let's switch to B. Sorry. It's just the variance of the signal. So it's the lines are slightly more distanced from each other. So what you see is the black line. The black line is the true statistics, and the other lines are different statistics from different machines. In blue, the physics informed, and in red, the physics uninformed, so the data-driven ecostate. And we have also two different reservoir sizes with 500 neurons and 1,500. So the bottom line again is that enforcing the physics in this case for 1,500 neurons retrieves almost exactly the statistics, which is good news, because having a machine that learns from relatively short time series of around 10 Lyapunov exponents in this case, we can basically extrapolate and learn the long-term behavior. And this is for the short-term prediction. So we saw first long-term prediction for the statistics. We saw that the effect of physics is noticeable. Now we look at the short-term prediction. So we look at how far in the future we can predict, and what is the effect of constraining the physics for the prediction of extreme event, of one extreme event which is coming. Once again, let's focus on one frame only for the sake of clarity. For example, this one, which is perhaps the clearest here. In this case, we have again one state variable, and we have the black, the data, the truth, PI-ESN, the physics-informed machine in blue, and the ecostate in red. So the extreme event we would like to predict is this one. This is the extreme event because it happens let's say it's sufficiently violent for us to consider it an extreme event. It's perhaps more apparent if we plot other state variables, but this one is the frame we are going to focus on for this discussion. So a couple of things. Well, the blue line is close to the black line, so that means two things. First, we can time accurately predict the event coming, which is one piece of information we wanted to be able to predict. And the second piece of information is the amplitude. We are able to predict satisfactorily the amplitude of the true solution. Perhaps the most striking thing is that if we don't constrain the physics, well, it looks like time accurately the signal is still somehow changing at the right moment, but the amplitude is just not captured sufficiently. Of course, this is a selected example to make the point, but in the paper we have done a more extended study. I just picked one frame to make the point in this discussion. And also the next question we asked is, okay, in these results we had let's say non-noisy data. So the data we were training the machine with was exactly deterministic, coming from a reference time integration. So in the second question we asked was, okay, can we do the same thing by having noisy data, which is the more realistic scenario? And the answer is yes. Overall, of course, noise makes things more less predictable, of course, because it kicks in chaotic effects more violently. But looking at, for example, now this frame, if we consider this event here as, let's say, a large amplitude event, with the blue line, which is the physics informed, is able to overall recreate the occurrence of the event, whereas the conventional ecostate doesn't. Now, one note, after the event, let's say, has occurred, we see that even the physics-informed starts diverging from the real dynamics. So that's something that we would expect, in my opinion, because again, that's the chaotic nature of the signal. So there, the sort of a butterfly effect, because of the strong nonlinear shaking, extreme event is making the trajectories diverge, even in the physics-informed echo state. And for a more scenic sort of video, this is the truth solution, and this is the physics-informed echo state. And we are comparing the vorticity and velocity fields side by side, and especially for the same, exactly the same time. And just qualitatively, you can say that let's say the violent dynamics, the extreme event, is captured in the same time and overall with the same topology of the flow. All right. Yeah, I'll skip over, sorry, because I just realized I'm running over a little bit. There was also another architecture we looked at, which is the automatic differentiated physics-informed echo state network. And that was applied to learn variables which we are not measuring through the observables. So for example, given an array of data, we might be unable to measure all the variables of the problem, but we might be still interested in reconstructing the unmeasured or hidden variables given what we measured. And that was the scope of the automatic differentiated physics-informed network. But I'm gonna skip it because otherwise I cannot finish what I would like to talk about. Okay, so let's go to the second topic. This is quite different in terms of application, but we're going to leverage on the capability of the physics-informed echo state network to learn the statistics of the signal from a relatively short data. So that's, from an engineer's perspective, is a very attractive thing to do. So let's talk first about the system we are going to analyze, the application. So, whoops. Okay, so you see here a rocket engine. This is a big rocket engine. It's the Saturn V in the Apollo 11 mission back in the 50s and 60s development. And now you see an explosion. So that explosion is caused by thermoacoustic instabilities. Thermoacoustic instabilities happen when the flame or the heat released by the flames, which are inside the combustor, synchronize with the acoustics of the combustor, which is a closed environment. When that constructive feedback happens, the oscillation is so powerful that can literally destroy the motor. Back in the 60s, sorry, NASA, the way they, which was NAC, I think, in the 60s, I'm not entirely sure, but how they dealt with the problem was actually to build 2,000 to 3,200 full-scale tests, so full-scale tests of real engines, until they would find the optimal configuration that wouldn't explode, wouldn't have thermoacoustic oscillations. And the way they did that back in the day was by trial and error. They would have hundreds of injectors, the geometry of the rockets, and they would change a little bit the geometry to see what happens. They would retest it, maybe it explodes again, and then they would retest, it would change the configuration again, and so on and forth. So interestingly, the physics behind the thermoacoustics, we cannot tackle the entire rocket with a model, but we can tackle the small flame. So if you put a camping gas flame in a tube, for some locations, the flame will become noisy. So the environment will become noisy. So we can actually focus on this problem, which is more manageable for some computational tool development. And that's what we're going to do now. This is relevant with afterburners in a military aircraft, rocket propulsion, civil propulsion with gas turbines, and also anytime you have a heat source inside a confined environment, even in boilers, if you like, or furnaces. Let's talk briefly about the model. So the model is, we have a tube with a compact source. So the model that works in the literature is just a longitudinal acoustics, so momentum equation in the longitudinal direction, and energy equation forced by the heat released by the flame, Q dot. So Q dot is the crucial parameter here. Q dot should be calculated, for example, by chemistry calculations, compressible Navier-Stokes with chemistry calculations, which are gigantic. So what we do in practical, in reality, is we use a simplified model for the heat release with two parameters that they contain all the essential physics of the problem. So the heat release can be shown to be a function of a function which has a strength, so a proportionality factor beta, and it's a nonlinear function of the acoustic velocity u in the past, tau units back in the past. So why is that? Broadly put, because when we have an oscillation at the base of the flame, which is what the acoustics is doing, this wrinkling of the flame takes approximately a time tau to develop altogether, which means the heat release Q dot is perturbed in a time tau approximately. So that's the broad justification of this model used in industry and many other scenarios. So we want basically to design a problem. We want to design a thermoacoustic system which is stable. And we want to tackle chaotic simulations because thermoacoustics can be chaotic. There is turbulence dominating the hydrodynamics, and also the nonlinearity of the heat release can create chaos. So we want basically, from an engineer's point of view, we want to be able to, given the time averaged energy over a long time, we want to be able to minimize this time averaged energy, which represents the acoustic oscillation. And the problem, as we have already appreciated at the beginning with the Lorentz system, is that if we try to do a gradient-based optimization of this energy, so taking the gradient with respect to the parameter S, because the gradient lives in the tangent space, the gradient grows indefinitely exponentially. So it's the usual way we optimize systems with gradient-based problems and algorithms cannot work as they are in chaotic simulations, in chaotic systems. There are ways to regularize the problems, which prove to be very elegant and successful, but they have some challenges in terms of computational cost and some also mathematical assumptions behind them. So the idea that we wanted to take advantage of from the machine learning we discussed today is, given a relatively short data set, for example, from 2 to 4 Lyapunov times, that's relatively short time series. In this time series, we wouldn't be able to calculate the time averaged statistics in the long term because it's too short, the data. But can we learn the dynamics and extract basically the evolution in time with the physics-informed or ecostate networks in general? We have some hopes that this can be done because we already saw in the Lorentz system that we were able, in the small turbulence system, that we were able to actually retrieve the statistics of the signal. So that was the underlying motivation to transfer the technology to a thermoacoustic realistic problem. So yes, we apply the physics informed to the thermoacoustic problem. I will skip over this slide. This slide is telling you that the short-term predictions are improved by the physics informed ecostate networks, which we knew already. And interestingly, what we can do as well is to study how well the machine is learning the signal in the long term. So when we let the machine evolve autonomously, how well is it learning the signal again in the long term? So how do we measure a signal in long term? One way is, for example, to calculate the spectrum of the signal. In this case, we compare 3 machines. One is the, let's say, the truth in green, the data-driven ecostate networks, and a physics-nudged, in this case, hybrid ecostate network in which we enforce the physical knowledge. Well, in this case, the spectra are overall well captured by the 3 machines. What is more perhaps informative is to look at the joint PDF, so the joint probability function between the first Fourier modes of the mu is the velocity and eta of the pressure, or the other way around. Sorry, I don't remember the notation, but it doesn't change much my point. The point is that the PDF between the two variables, which are two of the stated variables of the problem, is better captured when we inform the machine with the physics with respect to when we don't. And this is repeated for the joint PDF of the second Fourier modes and third and so on. So constrain the physics is able to learn the long-term dynamics better than without doing the constraint. So I'll just jump to the results here. I will very briefly explain what Francisco, my student, is working on. So because we are able to learn the dynamics of from small data, relatively small data, the long-term statistics from small data, we thought about using this capability to optimize a chaotic thermoacoustic system. And by optimize here, I mean finding the right set of design parameters, in this case, beta and tau of the heat release model, such that the time averaged acoustic energy is minimal, which is really the objective. We used a hybrid approach with ecostate and Gaussian processes to sample the space, but I don't have time, unfortunately, to go through that. I will just show the results. So what you see here is the time delay, the parameter we want to optimize, and in the horizontal axis, there is beta, the other parameter we want to optimize. This is the averaged, in the color, you see the averaged acoustic energy, time averaged acoustic energy, and this is the variance from the Gaussian process. And this is the acquisition function, which is the function that tells us where to sample next the parameter, the physical parameter space. So we start from this oscillation. It's unstable, it's noisy, it's also chaotic. We sampled the space with 4 points, seed points to start the Gaussian process. And then with this automatic gradient-free optimization, we evaluate the second point thanks to the acquisition function, and we evaluate the signal in time with the reservoir computing approach. The signal is still unstable, so we haven't optimized yet. We continue so evaluate the time average, evaluate the variance, evaluate the acquisition function. The acquisition function tells us which point to sample next, and then we sample that point and we continue. We continue until we find another interesting solution that I will play. So this solution is less energetic. We continue until some criterion on the iteration, and we finally find. This is not completely silent because there is a chaotic underlying dynamics, but it's a stable system, so it's not a tonal kind of energetic structure that is appearing. Right, so time is over. I cannot talk about turbulence, but if you give me 2 minutes, I'll wrap up as soon as possible. With the things we saw so far, we were able to tackle mathematically ordinary differential equations, so something that the derivatives of which appear all in time in this case. But turbulence, the real turbulence, is both a spatial and a temporal phenomenon. So ecostate networks themselves are not designed to see spatial correlations. They are designed to see temporal correlations. So to tackle turbulence, we propose therefore to use the ecostate network capability of extrapolating in time or learning time dynamics. And we use an auto-encoder based on convolutional neural networks, an auto-encoder that learns the latent space, so the structures, the nonlinear structures that are governing the spatial dynamics, the latent space of which the code is then time propagated with the ecostate and then reconstructed by the decoder or the upsampling part. And perhaps I just show this video to conclude. We've done some studies, and this is the truth signal, and this is the auto-encoded echo state network, and this is for one Reynolds number, mild turbulence, say, and this is for a more turbulent flow. This is not the realistic time. The time is slowed down for visualization processes. So qualitatively, you see that the machine is learning the turbulent dynamics. We also studied the statistics, and we were able to retrieve it. And there are more quantitative studies, of course, I can also explain later. Okay, yeah, sorry for overrunning. Anyway, to conclude, what we knew already is that chaos is tough because of, you know, even if it is deterministic, it's difficult to predict whether it's time accurately prediction or also in some sense statistical prediction, because we need a long time series. Now, physics informed and machine learning together, the synergy is far better than just the physical model and the machine learning models separately. We showed, in particular, physics-informed echo state networks for short-time prediction, long-term prediction, filtering out noise as well. We didn't have time to show the reconstruction of hidden variables, but that's another capability. And we saw, as an example, a gradient-free optimization of a thermoacoustic system. And the auto-encoded echo state is something that generalizes the echo state to spatially varying fields, like, for example, turbulent flows. Right, so I'll just stop here and leave the last slide just for visualization. And thank you for your attention. And if you have any questions, I'll be glad to attempt to answer.
Thank you so much, Luca. And thanks for the very illustrative presentation. And also it's really interesting work. So we have some time for 1 or 2 questions. And if you'd like to do so, you can ask your question by raising your hand, which I believe is in the chat section. So, do we have any questions? All right.
Oops.
So, whilst some people are thinking of their questions, I maybe ask one overall question. So obviously the advantage of, you know, considering both physics and machine learning models, not separately but together, is, as you showed very clearly, data efficiency. But can you comment also about the interpretability that this has, you know, allowed in your examples, in both your examples?
Yeah, that's a great question. Now, the short answer is we didn't look into that, and the short answer is we pay for a fee, meaning that I mean, inevitably we will go into the you know, for example, the autoencoder or the echo state itself is a higher dimensional system with you know, sparse dynamics, which somehow is randomized. So we lose a little bit of interpretability. I mean, I don't think there's nothing we can do about that. But what we might learn or improve, sorry, what we might improve is a better interpretability if we were able to open up the machine, which we are able in principle, and see the structures that the machine is learning. We haven't done that yet. What we are looking now with Anqua, we are looking at basically what is the auto-encoded echo state network, what is the latent space being learned, because that was already studied from other people, and it seems like that has a lot of physical structures, coherent structure as far as turbulence is concerned. So I cannot answer your question from what I've done, because we haven't done that yet. But certainly the machine is learning some physical structures which can be interpreted in the future.
Yeah. So we have a question here from Indir. Have you considered using Taken's embedding theorem for learning the latent embedding?
Yeah. I mean, yeah, Taken's theorem is really, I mean, a fantastic tool for, you know, try to reconstruct a signal. We considered that. We haven't done that. We were, you know, driven by basically trying to do that with a machine learning approach. We had a reviewer asking for that in some papers. So I think it's always valid. I don't think, I mean, Taken's theorem, it's you know, maybe solves from some course of dimensionality as well. So maybe it's not going to be possible to deploy it for, you know, high dimensional systems, which is what we ultimately always keep in mind to do. So yeah, we haven't done that. I cannot comment on that, but I don't think it's the way to go for real turbulent systems.
All right, thank you so much. If no one else has any further questions, because your presentation was so clear,
thank you.
Then I guess we can wrap up. And again, I'd like to thank you once again, Luca, for joining us and for sharing your work. And it was really, really interesting. And yeah, thanks for taking the time.
Yeah, my pleasure. Thank you very much for having me here.
Ciao. Bye.
Ciao.
Bye.
Bye.
Bye, everyone.